Let's try a different kind of problem. This problem says I've got two urns. One contains 2 red balls, 3 green balls, and 4 yellow balls. The other contains 4 red, 2 green, and 3 yellow balls. If a single ball is drawn from each urn, what is the probability that both are red? So I generally just like to sketch out those urns so it's right there in front of me. I can see what I have to look at graphically. Go ahead, stop the video, try and solve the problem. Then start the video, see how I did it, and compare it to how you did it. Let's take a look here. I've got 2 draws, one from each urn. For this both red scenario to come out, I need to draw red from the first urn and a red from the second urn. So I know I'm going to use a conjunction rule for this problem. I ask my rule for conjunction. Are these 2 events independent? Yes, they are. All right. What I draw from the first urn doesn't affect what I draw from the second urn, and vice versa. So I know they're independent. I can use that restricted conjunction rule. So now I have to estimate the probability of drawing a red from each urn. I'm going to use the classical theory of probability because I've got 9 balls in each urn. Presumably, I'll reach in, I'll move around, I'll pull one out, so every ball is just as likely as every other ball to get picked, and so the principle of indifference holds. And so now I can plug the numbers into my formulas and I'll get this. The probability of drawing a red on the first and a red from the second urn is going to equal the probability of drawing a red from the first urn times the probability of drawing a red from the second urn. Using that classical interpretation, the probability of drawing a red from the first urn is 2 divided by the total number of balls, which is 9. So 2 over 9 times probability of drawing a red from the second, 4 over the total number of balls, 9, 4 over 9. So 2 over 9 times 4 over 9 equals 8 over 81. Or if I did it in decimals, 2 over 9 is 0.222 approximately. 4 over 9 is 0.444 approximately. When you multiply them, you get 0.0987 approximately. Let's try another problem. Again, I've got these 2 urns, and it now asks me what's the probability that I draw at least 1 green. So at least 1 green. Again, stop the video, try and solve this problem yourself. Then, when you think you've got the answer, start the video, compare what you did to what I did. So at least 1 green I could get by drawing a green from the first. Or I could draw a green from the second urn, and that would give me at least 1 green. Or I could draw a green from both, and that still gives me at least 1 green. All this says I have to have a minimum of 1, so I could still have 2. So I know I'm going to use a disjunction because it's green or green. So I ask my disjunction question. Are they exclusive? That is, can I draw a green from the first urn, but not from the second then, or from the second urn, but not from the first? No, I could draw a green from both. Still works. So they're not exclusive. So I use my general disjunction rule. So now I need to estimate the probability of drawing a green from each urn. Again, I'll use the classical interpretation and plug those numbers into my general disjunction rule. So now I say, okay, look, the probability of drawing a green from urn 1 or a green from urn 2 or both is going to equal the probability of drawing a green from urn 1 plus the probability of drawing a green from urn 2 minus the probability of drawing a green from both urns. Remember, we have to subtract out the conjunction for our general disjunction rule. If you don't remember why that is, you might want to go back to that module and review it really quick so you make sure you know what you're doing when you're solving these problems and choosing between general and restricted disjunction rules. Now I plug my numbers in. 3 out of 9 for green on the first, plus 2 out of 9 for green on the second, minus the conjunction would be 3 out of 9 times 2 out of 9. And that will give me, adding these together, 5 over 9 minus 6 over 81. I have to convert this all to an 81 denominator, and I get 45 over 81 minus 8 over 81, and that gives me 39 over 81 as my solution. Let's do another one. One is red and the other is yellow. So now, again, stop the video. See if you can figure out this problem. When you think you've solved the problem, start it again. Compare what you did, how you set up the problem, how you solved it, to what I do. So I think about how to get one red and one yellow. And I say, okay, well, I could get a red on the first draw, and then I have to get a yellow on the second. That would be a favorable outcome. But suppose I don't get a red. Suppose I get a yellow instead. Then, if I draw a red, that's still a favorable outcome. So I have two ways of getting a favorable outcome. I can draw red on the first from the first turn, yellow from the second, or yellow from the first turn, red from the second. So I know now I've got to use restricted conjunction rule. That'll give me the probability of this first conjunction. And I'm going to have to use restricted conjunction rule to get the probability of this conjunction. The problem says this one or this one. So I'm going to have to use disjunction. Since only one of these can be the outcome of those two draws, I know that they are exclusive, so I can use the restricted disjunction rule as my final rule. So now again, using that classical interpretation, I plug my numbers into the formula, and I get 2 over 9 for red from the first urn times 3 over 9 yellow for the second urn, plus restricted disjunction, 4 over 9 yellow from the first urn times 4 over 9 red for the second. When I add these together, I've got 6 over 81 plus 16 over 81, and that's going to equal 22 over 81.